This is the Integrity Lecture for Nursing 227 over the Horntvedt Math Book, Chapter 16, regarding heparin administration. I would encourage you to take advantage of this lecture, and then I also have supplied you with a practice quiz, and that practice quiz would be a good way to assess your knowledge from this lecture and to see where you need to further study to prepare for the proctored quiz that will be occurring this week as well. There are some objectives listed on this PowerPoint, and I am going to skim over those. You can refer to these objectives when you are looking at the test blueprint for exam 2 in Nursing 227, and this will help to guide you with what type of heparin questions you can anticipate on that exam. When we talk about reasons that heparin would be administered, we often see that it's used to either prevent a blood clot from occurring inside of a vein. And so when we look at the different types of medications related to blood clots, there's two different types of heparin that we see utilized. And the first one is unfractionated heparin, which you will see abbreviated on the math quizzes as UH. And then there's a low molecular weight heparin, abbreviated as LMWH. When we talk about the low molecular weight heparin, we most often have this vocalized to us in practice as the enoxaparin, and the trade name for that is Lovenox. So that low molecular weight heparin is the Lovenox or the enoxaparin, and then the unfractionated heparin is most often just referred to as heparin. The main difference between these two types is their molecule size. So the unfractionated heparin is a very large molecule, and that enoxaparin or the unfractionated heparin is a very small molecule. The type of heparin that they will prescribe depends on your client's diagnosis and their condition. So we see both used very routinely. A lot of times the low molecular weight heparin or the enoxaparin is given subcutaneously. Once in a while it may be given IV. We do see the unfractionated heparin given both IV and subcutaneously. It's important to note though that neither type can be given orally because the stomach acids would not allow for it to be adequately absorbed. So it's either going to be given IV or sub-Q. Second thing to point out when we talk about heparin is to make sure you have the correct concentration. There are many different concentrations available, and so you really need to look at your doctor's order and ensure that you have the correct concentration. And so when we look at this slide, this just helps us to highlight and note that this one is 1,000 milliliter or units per milliliter, and this one is 5,000 units per milliliter. So giving 1 milliliter of each, this is 5 times the dose. 1 milliliter of this is 5,000 units, and this is 1,000 units. So it's really important to make sure that you have the correct concentration when you're administering heparin. Sometimes also there's something available in facilities called HepLock, and that's to help maintain that central venous catheter does not become occluded. And so you may see something like that used, and that has a much lower concentration here. If you look, it's 10 units per 1 milliliter. If we're going to give the heparin via an IV route, a lot of times they will put X amount of units into a 500 or 1,000 milliliter bag of fluid. One of the things to keep in mind when you administer a medication like heparin is to make sure that you're not only giving the correct concentration, but you're also giving the correct dose, and you've drawn up that syringe to the right mark, and you're giving it to the right client. Of course, all of your same medication checks. But when we talk about a medication like heparin, a lot of times, depending on your facility policy, there may be a policy that you do need to have a second nurse double check that you have the correct concentration, you've drawn up the syringe to the correct spot, and you've completed the correct math to give them the correct dose of medication. It's a high alert type of medication to make sure that we're preventing any type of medication error. So when we talk about what the route of administration will be, it's important to know if you are giving the low molecular weight dose. Sometimes you'll have a multi-dose vial, but a lot of times we see a pre-filled syringe. And so you want to, again, make sure that that syringe is the correct concentration and that you're giving the correct dose. All right, so here's our first example. A provider orders unfractionated heparin, 5,000 units, subcutaneously every 12 hours. The pharmacy provides a vial of unfractionated heparin with a concentration of 5,000 units per milliliter. How many milliliters per dose should the nurse draw into the syringe? Round to the nearest hundredth mil. So here's our question. How many milliliters per dose? So we are looking here for milliliters. So since we're starting out our problem looking for milliliters, we know milliliters has to be the numerator of our first equation. So we need to see what from our problem includes milliliters. And if we look up, the provider ordered 5,000 units. That's not it. And if we look here, 5,000 units per milliliter is what's available from our pharmacy. Again, this is your married equation. You can't separate this. So we're going to go ahead and put this 1 mil over the 5,000 units. Our next step then is we've got units here. We know that our answer is looking for milliliters. So how are we going to be able to reduce units? We can reduce that by entering another label of that same type as the numerator of our next equation. So then we can go ahead and let's look back at our problem, and we can see that the provider ordered 5,000 units. That's another example of that given quantity. That's what our healthcare provider has told us. And so then we can cross out our units, and we're going to take 5,000 divided by 5,000. This was a pretty easy one. You're going to get 1 milliliter. Let's look at another example. This provider is ordering 18,000 units subcutaneously once daily. You have the vial that contains 20,000 international units per milliliter. How many milliliters per dose should the nurse draw into the syringe? All right, so we are again looking for milliliters. We're going to go ahead and set up our equation with milliliters to the left. We're going to make our equal sign. And since we've got milliliters here, we have to start out with milliliters here. Now is when I look to my problem and I look and identify, we've got international units, and here we have international units per milliliter. So here's your marriage, has to stay together. We're going to go ahead and take our 1 milliliter, and then you would put that over your 20,000 units. We're looking for milliliters again, so we've got to figure out a way to eliminate or reduce this unit label, and we know we can do that by adding it as the numerator on this next, we're solving for x here on this next equation. So since we had units here, you have units here. You can see in the Horntvedt book, they're kind of going back and forth between labeling as units and labeling as IU, and IU is international units, and so just be free with that. Most of the time I do write out units because IU could be misinterpreted as a different label. So I would get in the habit of just writing out units to label with, but in this example we do see that the book has used IU, and don't let that throw you off. It's just a little inconsistency that they're presenting. So then we can go ahead and we can eliminate our units, and we would take 18,000 divided by 20. When we pop that into our calculator, we see that we would then administer 0.9 milliliters. So a great example for practice here would be, don't grab a 3 milliliter syringe. If you're going to give a small volume, less than 1 milliliter, you would want to grab a TB syringe because that has a greater accuracy of the dosage that you can draw up, and so it would allow you a more precise measurement. I'm going to skip over this next example. These are a little bit more basic. I'm going to let you do this one for practice, and you can double check yourself with my math, and then here's 3 more practice problems for you. Okay, so we talked about that heparin can be given IV or subcutaneously, and so sometimes we'll have a healthcare provider that will order a intermittent dose or a bolus dose of medication, and then we'll start a continuous infusion. And so when we talk about that, we're going to see different types of orders. This example states that the healthcare provider has ordered a heparin bolus of 60 units per kilogram intravenously prior to initiating a continuous infusion. We've got a client's weight in kilograms, and then we see that the pharmacy has provided us heparin with a concentration of 5,000 units per milliliter. So let's break this down and let's look at the first part. How many milliliters of heparin should the nurse draw up for the bolus? And so when we look at that bolus dose, we want to first decide what is that one-time dose of medication that we're going to administer. So when we look at that, we need to decide what we're looking for. And we're giving a medication that has a volume, so we're looking for milliliters. We'll go ahead and we'll copy that over here, and we've got our 1 milliliter over 5,000 units then. When we look at our next step, we are left with units here. Again, we can double check that we're looking for only milliliters, so we need to somehow deduce that label. And then we can do that by adding in units up here. So we can go to this next step without my messy scribble. And when we look back at our problem told us that we had a dosage of 60 units per kilogram. So since I have units down here, I know units needs to go up here. And often I write that in before I even start to enter my numbers, because that helps me to keep my mind straight, to make sure that I keep units as my numerator. And then I can go ahead and enter my 60 over my 1 kilogram. All right, so we've gotten rid of our units. Now we have kilograms down here. Again, our question only wants milliliters, so how are we going to get rid of kilograms? We get rid of kilograms by making that the numerator in our next equation. And when we look at our problem, the client's weight was 61 kilograms. So we enter 61, and we've then eliminated kilograms and we've eliminated units. We would take in our calculator and take 60 times 61 divided by 5,000, and our answer is 0.732. Now, when we look back, our problem wanted us to round to the nearest hundredth. So we would look at that thousandths place. It is less than 4 or less, so we would stay at 0.73 milliliters. Again, if you were going to drop a dose of 0.73 milliliters, anytime you're using that hundredths place, you're always going to use a TB syringe, because there's no way to measure the accuracy of the dose if you have a 3 milliliter syringe. Those are not, they don't have the hash marks to go down to the hundredths place. Okay, so a provider orders a heparin bolus dose of 80 units per kilogram IV prior to initiating that continuous infusion. Client's weight is 96 kilograms, and our pharmacy gives us heparin, and the vial says that there's 10,000 units per milliliter. How many milliliters of heparin should we draw up for this bolus? So again, we are looking for milliliters. How many milliliters? So we're going to start out our problem with milliliters here. We know that milliliters has to be transferred over, and that has to be the numerator in our first equation. When we look back to our problem, our given information is that we have 10,000 units per milliliter. This is your marriage, has to stay together, has to stay and be presented in one equation here. So we've got 1 milliliter over 10,000 units. Again, our question is only asking for a label of milliliters, so we've got to figure out how are we going to get rid of units. We can get rid of units by putting it up as the numerator in the next equation. So we've done that up here. When we look at our given information, I write units first, and then I look to my problem to identify what contains units, what goes next. And so then I would probably write units over kilogram, and then I fill in my 80, and I know that 80 goes with my units, and I know that 80 units per kilogram is that marriage, and it has to be presented in the same equation. So we've eliminated our units, but now we've got kilograms. So how are we going to get rid of kilograms? We'll do that by putting kilogram as the label of our next numerator, and our client weighs 96 kilograms. Again, if it confuses you to not have this with a denominator, go ahead and make your line and put over x and pretend like you're solving for x. Sometimes students find that helpful. So we would just type into our calculator 80 times 96 divided by 10,000, and our answer would be 0.768. Again, our instructions were to round to the nearest, to the hundredths place, so that's this right here. So we need to identify what number is in our thousandths place, and so it is 5 or greater at an 8, so we would need to round up. So our answer would be 0.77 milliliters. It's very important, if you haven't learned by now, to pay attention to your rounding instructions. When you guys take your NCLEX exam, you won't be able to have credit if you round to the wrong problem, or to the wrong spot. You just get that problem wrong. So really start following directions, paying attention to what your rounding place is. A lot of times we have a standing type order or a flow rate calculation when we talk about when we would be or how we would administer heparin. And so this is just an example of a weight-based heparin protocol. And so then what you would do is you would interpret your lab results. And if your lab results were, let's just pretend between, maybe our lab result was 140, then you would not give a bolus and you would stop your infusion for 30 minutes. And then when you restarted it, you would decrease your rate by 200. You see these in areas such as the intensive care unit or a specialized cardiac floor. So these aren't things that you're required to be competent with right out of school, but it's something that you need to understand is an available working tool, and that's what guides the nurse in this type of an area. So when we talk about giving heparin IV, we're looking here at some different premixed concentrations that we see most commonly in practice. A lot of times we'll see that a certain facility will only purchase one concentration, and they have that all throughout. That helps so that if you're floating to a different area, or if you worked with a concentration of 25,000 units one day and then the next day you're using a 2,000 unit concentration, you're not giving the client the incorrect dose. So we just see this for consistency, but you may work at a facility someday that has multiple concentrations. So again, as you think of the safe ways to administer drugs, you're always going to make sure that you have the correct dose. So when we talk about heparin administration, a lot of times we see that a flow sheet is used so that you can easily keep track of how the dose has been titrated. And a lot of times you will have nursing that will be calculating and adjusting that flow rate independently. They'll have the doctor's order like we saw on that flow sheet, or the what we want it to see, but then you're in charge of actually titrating that dose going to the client. A lot of times, or most times when we use a heparin IV administration in an acute care setting, you will be using what we've talked about before as the micro pump. So when you use a micro pump, it's a little bit more accurate way you can administer the medication, and we then would be rounding to the nearest 10th milliliter. And so in a lot of the problems this week, we're going to be rounding to the 10th milliliter, and that would just indicate in practice that you would know you needed to grab a micro IV pump or a little bit more of a specialized accurate IV pump. Okay, when we look at this problem, we've got a healthcare provider that's ordering a continuous heparin infusion, and they have ordered it at 18 units per kilogram per hour. You've got a client in the bed that weighs 59 kilograms, and your pharmacy gives you this bag of fluid that says it has 25,000 units in 500 milliliters of solution. So let's calculate our milliliters per hour flow rate, and then we're going to round to the nearest 10th milliliter. So that's a lot of words. Let's break it down. What are we looking for? We want to know how many mils per hour are we going to set that pump at, and that's what we're looking for. So this is why dimensional analysis is the best way to use. We're going to just identify mils per hour. Again, we need to put milliliters over hour. Our numerator of what we're looking for is milliliters. All we need to know at this point is that we're looking for milliliters, so we're going to take and we're going to start with milliliters here. I know my first label is going to be milliliters, so at this point I'm not even looking at this. I'm just going to look up to my problem, and I am going to identify what from my problem contains milliliters. When I look up and I do that, I can see that one of my given quantities is what pharmacy is giving me. And pharmacy says there's this bag of fluid they've brought me. The bag tells me that there are 25,000 units of heparin in 500 milliliters of fluid. So I know that milliliters goes on top. I'm going to put my 500 milliliters over 25,000 units. This bag of fluid is married. It can't be separated. The pharmacist put, or the drug company put, this much heparin in this many milliliters, so those can't ever be separated because we aren't adding more medication or more fluid. Those numbers need to stay together. So we are at this step right here. So our answer is asking for milliliters per hour. We're left with units here. So how are we going to get rid of units? We're going to get rid of units by putting units up here. Now I want to look to my problem and see what from my problem talked about units. Well, my healthcare provider told me that I was going to give 15 units per kilogram per hour. I'm not an advanced practice nurse that can prescribe or change orders, so I know that this needs to stay together. 15 units per kilogram per hour. I can only ever have one label as my numerator in dimensional analysis. However, I can have two labels as my denominator. So when I'm looking at a 3-part label like this, I need to be able to identify that I can have kilograms per hour on the bottom, but I can only have units on the top. So it's important to note that when you write this, your 15 units goes over your kilograms per hour. Now, since this was all presented together from your healthcare provider, you can't break this up, and that's one of the ways also to remember. I can't put hour over here as a denominator in a different equation. That's not an option because my healthcare provider had that all together, and so I have to keep that all together in this equation here. When we then look at our next step, we've eliminated units and we're left with kilograms per hour. So now what we need to do is look at what we're looking for. So we have milliliters here, and our problem is asking for hours. So I don't need to change or do anything with this hour label. That's perfect, but I need to get rid of this kilogram here. So how am I going to do that? I'm going to do that by making my next numerator a kilogram. And so our client's weight was noted at 59 kilograms. If you need to, put it over X if that helps you remember to multiply 59. So then what we're going to do is just enter this data into our calculator. We've reduced these labels. We're left with milliliters per hour, so that's looking good. Let's take 500 times 15 times 59 divided by 25,000. And we happen to get an exact answer of 17.7. We would label this as milliliters per hour. And when we look back at our rounding directions, they indicated we should round to the nearest tenth. So we didn't even need to remember our rounding rules. Our answer would be 17.7 milliliters per hour. All right, let's do another one of those. You are now having a healthcare provider that orders a continuous heparin infusion to begin at 16 units per kilogram per hour. Your client weighs 88 kilograms. Your pharmacy gives you this bag of heparin. The concentration is 20,000 units of heparin in 500 milliliters of D5. Calculate the milliliters per hour flow rate. So right now, all we have to know is what we're looking for. We are looking for milliliters per hour. So we're going to write that as an equation here. Since we are looking for milliliters in our equation numerator of what we're solving for, we have to start out our problem with milliliters. At this point, all I've got written on my paper is this line and milliliters. I need to look up to my problem and decide what has milliliters. When I look at what the pharmacy sent me, that has milliliters, and I know that the 500 milliliters has to be in an equation with 20,000 units because that's what the pharmacy has given me. And so we have then 500 milliliters over 20,000 units. So we have units on the bottom. How are we going to get rid of units? Our question's not asking for a label that contains units. So that's our key, that we need to somehow reduce units. So we're going to go ahead, and in our next step, we know that we're going to have units up here. And I can't spell while I talk, apparently. All right, so all I've got so far is units here. Now I'm going to look up to my problem. I'm going to look up to my problem and decide what has units that I haven't used yet. And my healthcare provider ordered 16 units per kilograms per hour. Now, remember, we can only have one label as our numerator. However, we can have two as the denominator. So we can have kilograms per hour both in this denominator of this equation. When we look at what our label is we're looking for, we need to keep hours because that's what we're going to use to know that we're accurately setting our pump. But we don't want to keep kilograms. So we need to go back and decide how we're going to get rid of kilograms. We're going to get rid of kilograms by putting it as the numerator in our next equation. We can put that over X. And then we've reduced all of our labels that we don't need. And we're going to take 500 times 16 times 88 divided by 20,000. And we have a volume of 35.2 milliliters per hour. Don't even need to reduce that one either because our directions were to round to the nearest tenth. So that's just what we did. All right, we've got a couple more practice problems here. I'm going to let you review those on your own. And now what we're going to do is look at a flow rate. So a nurse is verifying the dosage of a heparin infusion. Your IV pump is infusing at 13.7 milliliters per hour. Your bag that's hanging from pharmacy tells you that the concentration is 20,000 units of heparin per 500 milliliters. And then I'll just highlight this because we need to know this. 13.7 mils per hour is what our pump is set at. Our question's asking us, how many units are infusing per hour? So we're going to double check, and we want to be able to identify if the doctor's order is being carried out. This is a way to double check our math. So we're looking for units per hour. Units over hours. Since we are looking for units as the numerator in what we're solving for, we have to start out with units as our label. At this point, all I've got written on my paper is this, a line, I have my equal sign, and I have units. Now I'm going to look up to my problem and identify what has units. When I look up at what I'm given, I have a bag of IV fluid that's labeled with 20,000 units in 500 milliliters. So that's my equation that has to stay together and cannot be separated. So I'm going to look at units, and I have 20,000 units per 500 mils. So I'm going to keep that together in this equation. Now I'm looking for units per hour, and I have milliliters. So something tells me I've got to be able to reduce or eliminate that milliliter as a label, because that's not added as a label of what I'm looking for. So since I have milliliters down here, I'm going to go ahead and put milliliters up here. Then I need to look to my problem and identify what has a label of milliliters. And it's my pump setting. My pump is infusing at 13.7 milliliters per hour. So I can go ahead and then enter my 13.7 milliliters over hour. Again, sometimes since there's not a number here, students forget that this needs to stay married, and they also forget that this is part of an equation. So I just want to point out to you that when we look at setting up this next problem, you again can never ever have two labels as your numerator. I've seen students where they'll try to put milliliters per hour as your all up on top. And so really anytime you have per, that's an indication that you're going to have a line. And you can't ever have two labels on the top of an equation. So there's only two labels in this problem, so there's going to be just one on top and one on bottom. Then we can go ahead and we can reduce our labels, and look at that. We're left with units per hour, just what we wanted. So we would take 20,000 units times 13.7 divided by 500. Your answer to this problem would be 548 units per hour. And there is another example of how you could do a problem like that. And so I'm going to let you do this example too, as well as these examples as ways for you to check and ensure that you would be able to identify how many units per hour are infusing based on what your pump setting is regulated at. When we look at adjusting heparin flow, a lot of times you're going to be titrating it up and titrating it down. And how we know how to do that is based on laboratory values. You would have some type of a flow sheet, and most of the time we see this on an electronic medical record now, but you may still have a paper copy in some facilities. And so this is an example of you would fill in the date, the time, what it's currently going at. So let's pretend it's 17.4. And then you would have this lab value, your PTT. If your PTT showed a value that indicated a bolus, that would go here. And then if you had a rate change, that would go here. You would then enter your new flow rate per your pump setting, and then you would initial an order when your next laboratory value would need to be obtained. And most of the time when we adjust these settings in our electronic medical record, the MAR will automatically be documenting all of this information for us. But we do know that electronic medical records go down, and so it is important that you differentiate and are able to identify how you would do the paper charting for such an occurrence. When we look at adjusting a flow rate, I have an example here that we'll go through. Continuous heparin infusion is infusing at 800 units per hour. According to the hospital's heparin protocol, the infusion should be decreased by 100 units per hour. The IV pump should be programmed to what new rate? And this is pretty easy. We can just subtract 100 from 800, and you would always have a calculator available to you on the floor as well as, in any practice setting. So you could just take 800 minus 1. This example here shows us that a client has a continuous heparin infusion running at 14.5 milliliters per hour. According to the heparin protocol, the infusion should be increased by 200 units per hour. The current bag hanging contains a concentration of 20,000 units in 500 milliliters, and the IV should be programmed to how many milliliters per hour? Round to the nearest 10th mil. So, a lot of information given in this one, but let's just look at what we're looking for. We have a pump in front of us, we have a patient in front of us. How many mils per hour should we set our pump to? So let's start out our problem with this. So we've got milliliters per hour. What do we know has milliliters? We have to keep this label of milliliters in that first numerator, and our concentration in our bag of fluid is 500 per 2,000. We have units here, and we're only looking for a label that includes milliliters and hours. So we need to somehow eliminate units. We know we can eliminate units by adding it as the label of our next equation in that numerator. And then when we look at what contains units in our problem, we can notice that the current flow rate is 200 units per hour. So we're going to go ahead and put 200 units over 1 hour. Then all we would do is take 500 times 200, divided by 20,000, and then we would have an answer of 5 milliliters per hour. When we look at then how you would complete that math, you would take your current flow rate of 14.5 and you would add 5 milliliters, and so 14.5 plus 5, your new flow rate then would be 19.5 milliliters. And we've got some more practice problems here with those types of problems. When we look at how we monitor the effectiveness of both types of heparin, it's important to know which lab values are tied to each. Most of the time when we have clients that are on the enoxaparin, we don't see routine lab monitoring unless they are in a special circumstance. And when we see clients that are on heparin or unfractionated heparin, we often will use the APTT lab value. So when we look at that lab value, we would look at measuring the time that it takes for a clot to form after that blood sample has been drawn. And so a lot of times you're going to have a little bit of a differentiation in your facility, and we know labs vary depending on textbook or facility, but your normal range is usually 25 to 39, and that's represented by seconds. And so when we look at that PTT, we want to look at that number, and that tells us then how thin or how thick the blood is. And so typically we see that when someone's on heparin, they're going to have a value of 1.5 to 2.5 times that normal value of 25 to 39. And this is often clearly identified on your orders as to what your target PTT would be for your specific client and the client-specific condition. Okay, I look forward to any questions or concerns that you have over these math problems, and I encourage you highly to do that math practice quiz in preparation for your proctored quiz this week. Have a fabulous rest of the day.